What if the moon never rose? Rewriting Earth from frame 1. What if the single object that may have made complex life on Earth possible never existed? What if, before page 1 of our planet's story, we quietly deleted the moon from the script? We are used to a very specific version of Earth. Calm, blue oceans breathing in and out with the tides. Predictable seasons that let forests, coral reefs, and civilizations plan ahead. Quiet silver nights where the moon hangs over everything, like a cosmic clock. But while that feels normal to us, it should be noted that this is just one way a planet can be. Erase the moon, and almost nothing about our familiar world survives intact. Imagine stepping outside on a young, moonless Earth. The nights are truly black, the stars sharp and cold. No glowing disk rising over the horizon, no gentle lunar tides pulling at the shore. The planet spins faster, so the day might last only a few hours. Winds scream harder, storms recharge more often, and the rhythm of sunrise and sunset feels more like a spinning coin than a steady heartbeat. Would such a world ever become habitable in the way we understand it? We often treat the moon as a pretty nightlight, but in reality, it is an engine. Its gravity grips our oceans and sculpts the tides, driving powerful mixing that stirs nutrients and shapes coastlines. Its pull acts as a brake on Earth's rotation, slowly stretching our days from a frantic early spin toward the 24-hour cycle life relies on today. And perhaps most crucially, the moon acts like a stabilizer bar, keeping Earth's tilt from lurching wildly over millions of years. This means our climate can settle into long, relatively gentle patterns, instead of swinging between brutal extremes. So remove the moon, and we are not just dimming the night sky, we are tearing out a structural support beam. Without that stabilizing torque, Earth's axis could wander like a drunken spinning top, tipping tens of degrees. Ice caps might melt and refreeze in unpredictable cycles. Continents could take turns roasting under a high direct sun, and then freezing in permanent twilight. In the hunt for alien life, we often focus on whether a planet sits in the Goldilocks zone around its star. But what if the real question is whether its spin and tilt stay calm for long enough for complex life to evolve at all? So it's time to find out the truth. On a moon-less Earth, do oceans still nurture biology for billions of years, or does our planet become a chaotic, perhaps lifeless rock? And if most of the exoplanets we discover do not have large moons, should we still call them truly Earth-like? By the end of this video, we will use real data and real physics to reach a verdict on whether creatures like us could ever arise under a moonless sky. So, let's begin. Why the moon matters more than you've been told so if deleting the moon changes everything. We have to ask a deeper question. How much of what we take for granted on Earth is just an accident of having this one, oversized companion in our sky? In the hunt for alien life, our own planet is the only confirmed success story. It should be noted that Earth is unusual in one striking way. For its size, it has a giant moon. Many astronomers now suspect that this is not just cosmetic. The leading idea is that a Mars-sized planet, often called Theia, slammed into the young Earth, and the debris in orbit eventually merged into the moon. This means the very event that created our satellite also rewrote Earth's early history. Why does that matter to us? Because that collision may have set the initial spin of our planet, reshaped its interior, and locked in an axial tilt that the moon has been stabilizing ever since. Without that steadying gravitational hand, Earth's axis could wander over millions of years, swinging from almost upright to dramatically tilted. Seasons, climate zones, even the length of the day would evolve along a completely different path. When we ask, what if the moon never existed? We are really asking, how fragile was the path that led to complex life? And this is not just about our own backyard. Most of the exoplanets we have found, even the ones we call Earth-like, do not obviously have big moons. Our telescopes are only just reaching the precision needed to see such companions at all. So a moonless Earth becomes a template. If a planet can stay habitable and stable for billions of years without a large moon, then many worlds in the galaxy might qualify. If it cannot, then truly Earth-like planets may be far rarer than we hoped. But while that sounds straightforward, the science is anything but simple. We cannot run Earth twice, with and without a moon, and compare the outcomes. So, scientists turned to simulations, to Mars, which has tiny moons and a wildly shifting tilt, and to clues frozen in our own rocks and fossils. Optimistically speaking, these models are improving, but every result comes with wide margins of error and fierce debate. So, let's begin to narrow this down. If the moon never forms, Earth's rotation stays faster, its axis less anchored, and its tides far weaker. However, ocean mixing changes, coastlines evolve differently, climates may lurch between extremes, and the biosphere has to adapt or fail under a sky with no bright disk to rule the night. So it's time to find out the truth. Does a moonless Earth spiral into chaos, or does it settle into a different, still habitable state? And what would that actually look like? Day by day, ocean by ocean. How we got a moon in the first place, and what if we didn't? To understand what a moonless Earth really means, we first have to ask a deeper question. How did we get a moon at all? Most of the evidence points to one violent answer. About 4.5 billion years ago, when the solar system was still a chaotic construction site, a Mars-sized planet we call Theia probably slammed into the young Earth. Not a glancing bump, but a world-shattering impact. Rock and metal were blasted into orbit, forming a glowing ring of debris. Within a few tens of millions of years, that debris merged into a single large companion, the Moon. In the process, much of Earth's outer layer was remelted, almost as if the planet was briefly reset. This collision did far more than just add a bright disk to our night sky. It should be noted that such a giant impact can rewrite a planet's basic settings. Theia's blow likely changed Earth's rotation rate, spinning it up so that an early day might have lasted only a few hours. It probably tilted Earth's axis to something like the 23.5 degrees we have now, setting up the pattern of seasons. And by mixing the interior, it may have reshaped the core, the magnetic field, and the inventory of water and gases that later became our atmosphere. This means that when we delete the moon, we may also be deleting Theia. In a no-moon timeline, maybe Theia never forms, or misses us, or hits at a very different angle and speed. The result? No large satellite in orbit, and a young Earth with a different spin rate, a different tilt, and a different internal structure from the very beginning. Before any ocean, before any continent, before any trace of life. Without that global remelting, early Earth's crust might solidify more gently, with fewer, worldwide, lava oceans. Continents could form earlier or later in different shapes, changing how oceans are distributed across the surface. The core might cool and stir differently, delaying or weakening the magnetic shield that protects the atmosphere from the solar wind. In the hunt for alien life, we care about these details because they decide whether a planet stays habitable or is stripped and sterilized over billions of years. Optimistically speaking, you could still imagine a moonless Earth that finds a stable path. But while our real Earth had its rotation, tilt, and shield tuned by a single catastrophic event, a no-moon Earth would rely on a slower, more uncertain path set by countless smaller impacts and internal processes. So, let's begin from that premise. This alternate Earth is already a different world before life even has a chance to start. So it's time to find out the truth. On a planet with no moon, do oceans condense, climates settle, and chemistry spark into biology? Or does the story of life on Earth end before it ever begins? Spinning without a break, days, nights, and a restless Earth. If we delete the moon, what happens to something as basic as a day? We often think of the moon as a light in the night sky, but in reality, it is also a brake pad clamped onto Earth's spin. Here is how that works. As Earth rotates, the moon's gravity pulls on our oceans and even on the rock itself, raising tidal bulges. Because Earth spins faster than the moon orbits, those bulges are dragged slightly ahead of the moon. That offset matters. It means Earth's rotation tugs on the moon, pushing it outward, while the moon's gravity tugs back, stealing a tiny bit of our spin energy. This tidal braking has been at work for more than 4 billion years, early in Earth's history, right after the giant impact that probably formed the moon. A day may have lasted only 6 to 10 hours. Since then, the constant transfer of angular momentum has gradually slowed us down to the 24-hour cycle that feels so natural today. It should be noted that this process is still going on. Laser measurements show the moon drifting away by about 3.8 centimeters per year, and our days are still lengthening by milliseconds per century. But remove the moon, and the story changes dramatically. Solar tides from the sun would still exist, yet they are much weaker and less efficient at braking the planet. Simulations suggest that in a moonless version of this same system, Earth's day could have remained much shorter for much longer. Even after billions of years, we might still be spinning through a full rotation in only 10 to 14 hours. So, let's begin to imagine living on an Earth-like world where noon comes twice as often. What does a faster spin actually feel like on the surface? Stronger Coriolis forces twist moving air and water more aggressively. Instead of the familiar pattern of a few broad jet streams, we could see many narrow bands encircling the planet with sharper boundaries between climate zones. This means storm systems might be smaller in size, but more intense, with rapid-fire weather changes sweeping across continents. Now add the rhythm of light and dark. On this alternate Earth, sunrises and sunsets would race by. A full day night cycle might last less than half of what we experience now. There is less time time for the surface to heat up during the day, and less time to cool down at night. Temperature swings could become tighter in some regions, yet more abrupt in others, subtly reshaping where deserts form, where clouds build, and how oceans circulate. In the hunt for alien life, these details matter. Life on such a planet would evolve under a relentless strobe of daylight and darkness, adapting internal clocks to rapid cycles rather than long, lazy afternoons. Optimistically speaking, that world could still be habitable, just different. But rotation is only half of the story. Without the moon's steadying hand, Earth's axis itself begins to wobble, and that is where the real chaos starts. The drunk spinning top, axial tilt, and climate chaos. So if rotation is only half the story, here's the other half. What happens when the entire planet starts to lean over? And, more importantly, could life keep up with a world that cannot decide which way is up? Axial tilt, or obliquity, is simply the angle between Earth's spin axis and its orbit around the Sun. Right now, we sit at about 23.5 degrees. This modest lean is why we have seasons at all. The hemispheres take turns being tipped toward the Sun, but the key point is that, over long timescales, those seasons are relatively predictable. Summer is always warmer than winter, the tropics stay tropical. It should be noted that this stability is not guaranteed by the Sun alone. Our moon acts like a giant flywheel attached to Earth's equator. Its gravity tugs on our equatorial bulge and damps wild wobbles, so the axis precesses smoothly instead of tumbling chaotically. In the hunt for alien life, this kind of long-term stability is pure gold, because models show that with a large moon, Earth's tilt probably stays confined to a fairly narrow band for hundreds of millions of years. But while Earth enjoys this lunar seatbelt, Mars does not. Mars also orbits in the same solar system, around the same star, but its two tiny moons are far too small to stabilize it. Simulations, backed up by geological data, suggest that Mars' tilt has wandered from less than 10 degrees to over 60 degrees. Imagine the Martian poles pointing almost straight at the Sun. Then, millions of years later, relaxing back toward upright, ice caps would migrate, frozen water and CO would shift toward the equator, and entire epochs could swing between relatively warm, wet conditions and deep freeze deserts. So it's time to find out the truth. What if Earth had no moon at all, without that stabilizing companion? The gravitational nudges from the Sun and from other planets in the system, especially Jupiter, would have a much freer hand. Numerical experiments show that a moonless Earth could see its obliquity meander by tens of degrees over tens to hundreds of millions of years. Sometimes we might stand almost upright, with weak seasons. At other times, we could tilt so far that the tropics slide toward what are now polar regions. This means entire climate zones would be temporary. Forests would be crushed by advancing ice sheets, then later replaced by deserts under a blazing high-latitude sun. Oceans would repeatedly freeze at the edges, then thaw and flood coastlines. Complex, land-based ecosystems would be forced into retreat, then invited back, again and again. Optimistically speaking, perhaps evolution would thrive on this pressure, but there is a darker possibility. Do you get intelligent, technological life on a planet that keeps hitting the reset button? Or does a moonless Earth become an evolutionary Groundhog Day, forever rebuilding complexity that never quite has time to mature? To answer that, we need to follow the water, the coastlines, and the tides themselves. Tides without a moon, silent oceans, different life. So if a moonless Earth keeps resetting evolution, what actually happens at the shoreline where so much of that evolution begins? Because to answer that, we have to talk about tides. Today's oceans move to a double beat. The sun pulls on our seas, but the moon dominates. Their gravity overlaps, sometimes lining up to produce dramatic spring tides, sometimes canceling to give neap tides. This means that in many coastal regions, we see tidal ranges of several meters, and with them fast, surging currents that slam through bays, estuaries, and narrow straits. Those flows are not just scenic, they are engines. It should be noted that these engines do real work on the planet. Strong tides drag water over rough seafloors, stirring up sediments, mixing warm surface layers with colder, nutrient-rich depths, and constantly refreshing oxygen near the coast. In places like the Bay of Fundy or the English Channel, the daily rise and fall of the sea is effectively a giant pump, reshaping mudflats, carving channels, and feeding dense, productive ecosystems. For early life, that constant churning may have been as important as sunlight itself. Remove the moon, and those engines idle. On a moonless Earth, only solar tides remain. The sun still pulls, but its tidal effect is weaker, typically. We would be left with tides roughly a one-third as strong as the combined lunar, solar tides we know. So, let's begin to imagine coastlines where the sea only creeps a little higher and lower each day, where tidal ranges shrink, and where many currents currents become sluggish shadows of their present selves. Vertical mixing in the open ocean would weaken, especially in deep basins. Some areas might stratify into stable layers, with nutrients trapped below and surface waters turning comparatively poor. But while weaker tides sound gentle, they also rewrite the script for life. Intertidal zones today are harsh training grounds. Twice a day, organisms are soaked, then stranded. They face crashing waves, drying winds, and rapidly shifting temperatures. This means only the hardiest survive. Barnacles glued to rock, algae that can desiccate and rehydrate, fish that wriggle between pools. Many biologists suspect that these fluctuating marginal environments could have encouraged the first tentative steps from sea to land through tide pools and periodically exposed shorelines. On a quiet, moonless coast, that drama softens. Fewer dramatic rock platforms emerge from the water. Tide pools are shallower, less isolated, less extreme. Optimistically speaking, life still adapts, but perhaps more slowly. The big evolutionary push to handle drying, gravity, and air might be delayed or channeled into different ecosystems entirely. Maybe our planet stays ocean-dominated for longer, with vast marine diversity and a slower, stranger colonization of land. In the hunt for alien life, that matters, because many exoplanets in the habitable zone may also lack large moons. So it's time to find out the truth. Does weaker tidal forcing doom complexity, or just redirect it? And here's the pattern interrupt. What if those ferocious tidal zones we celebrate were actually deadly minefields for fragile early organisms, and a calmer, moonless shoreline protected them instead? Perhaps a quieter tide does not mean a dead world at all, but a different, equally rich biosphere, just not the one we evolved in. Seasons on a world that can't make up its mind, so if the tides are calmer, the days are shorter. And the axis of our planet is free to wander. What does that actually feel like on the ground? Over millions of years, what is it like to live on a world that cannot quite decide where its seasons belong? So, let's begin with the quiet phases. In some stretches of deep time, a moonless Earth would likely sit almost upright, with a tilt of only a few degrees. This means the sun's path in the sky would hardly change with the months. Summer and winter would blur together. Near the equator, temperatures would be remarkably steady year-round, with only day, night cycles and ocean currents breaking the monotony. But at the poles, the story turns harsh. They would still spend long weeks in darkness and long weeks in low, grazing sunlight, yet without strong seasonal swings to melt accumulated snow. It should be noted that this is a perfect recipe for ice. Ice caps could grow, thicken, and persist, locking up enormous amounts of water. Sea levels might fall by tens of meters, exposing new continental shelves and stranding coastal ecosystems. Then, the axis wanders. Over a few million years, gravitational nudges from the sun and other planets could push Earth into a high tilt phase, 45, 60 degrees, or even more. Now imagine the North Pole leaning almost directly at the sun. For months, it would sit under a blazing, high noon star. Polar summer would be scorching, with the sun circling overhead and barely setting at all. Ice would retreat, tundra would bake, and what used to be frozen desert could briefly become a patchwork of rivers and forests. Then, the planet moves in its orbit, and that same pole swings into a deep freeze night, lasting many months. Temperatures plunge, oceans nearby lock under thick ice, and only the hardiest forms of life endure. Meanwhile, the equatorial regions might experience surprisingly mild, almost seasonless conditions, because the sun's average angle there changes less than at the poles. Across geological time, this chaotic dance of low tilt and high tilt eras would drive enormous climate cycles. Continents that were once temperate could be buried under ice sheets in one epoch and become dry. Wind scoured deserts in the next. Rain belts would migrate, monsoon systems would reassemble themselves, and coastlines would advance and retreat as glaciers waxed and waned. In the hunt for alien life, we often imagine stable, Earth-like climates as ideal. But here, complex, climate-sensitive life on land would be repeatedly pushed to the edge, forced to move, adapt, or vanish. Ecosystems would be torn down and rebuilt again and again. So it's time to find out the truth. Does this ceaseless environmental stress doom a moonless Earth to remain simple, dominated by microbes and hardy generalists? Or, optimistically speaking, could evolution use every wild climate swing as a stress test, innovating faster, exploring new body plans, and producing a biosphere that is harsher than ours, but not hopeless at all? What if the very instability we fear is exactly what unlocks the strangest, most resilient forms of life a planet can host? Wait, who am I, and where's the channel intro? So at this point, we've already spun up a faster Earth, stripped away its tides, and thrown its seasons into chaos, and only now are we asking, wait, who are we? And what exactly is this channel doing to the solar system? It should be noted that this little pattern break is intentional. We like to drop you straight into the deep end of a what-if universe first, and only then step back and introduce ourselves. We are a channel devoted to edge case worlds, planets that almost look Earth-like but fail one key test. No thick atmosphere, no stable orbit, or, in this case, no moon at all. Our mission is simple to say and hard to answer. We want to know how rare Earth really is, not just a rock in the Goldilocks zone of a star, but a complete system: rotation, tilt, oceans, and yes, big moons. In the hunt for alien life, that means asking whether a habitable planet without a lunar stabilizer is quietly disqualified long before we ever see it in a telescope image. So, let's begin to map out where we are in this story, and where we are heading next. First, we are going to finish building the physical picture of a moonless Earth. How fast does it spin without the moon's tidal breaking? How wildly can its axial tilt wander over millions of years? What happens to tides when the only pull left is from the sun? And how does that reshape climate, coastlines, and the deep ocean engine that our biosphere depends on? Once we have that physical scaffold, we will ask what life does with it. Does evolution stall out in a world of short days, weak tides, and violently shifting seasons, leaving a planet ruled by microbes and generalists? Or does biology treat every climate swing as a stress test, innovating faster, exploring new body plans, and perhaps even finding new routes to something like intelligence? Then we zoom out. We will take this alternate Earth and hold it up against the exoplanets we keep hearing about in the news. A world in the right orbit, with the right temperature, and a promising atmosphere might sound Earth-like, but without a large moon, is it really? So it's time to find out the truth about whether big moons belong on the same checklist as liquid water and a stable star. By the end of this episode, when you see a headline about a new Earth-sized planet in a distant system, we want you to ask a sharper question: but does it have a moon? And how much does that matter? As we go, try to keep two timelines in your mind: the Earth you know, and the Earth we are deleting the moon from. Follow them as they diverge, step by step, until we can finally judge whether our moon is a pleasant cosmic bonus, or very close to a requirement for an Earth-like civilization. Gravity, spin, and shields, the core physics you need to compare those two Earths properly. We need one more thing: a shared language for the invisible forces running the show. Without that, a missing moon is just a pretty picture, not a physical story. So, let's begin with gravity and spin. Gravity is simple at heart. Anything with mass pulls on anything else with mass. You feel it as weight, the Earth feels it from the sun, and the Earth and moon feel it from each other. Angular momentum is the keep doing what you're doing of rotation. A spinning planet resists changes to how fast it spins, or which way its axis points. But while these ideas sound abstract, over billions of years they quietly rewrite the surface and interior of a world. Tides are where gravity and spin start talking to each other. We often think of tides as ocean water, sloshing up and down twice a day. But the whole planet is actually flexing. The gravitational tug from a companion body stretches Earth into a slightly squashed shape, raising a bulge in rock and water. If that bulge is not perfectly aligned with the line between the two bodies, it tugs back. This means the bulge can act like a brake on the planet's spin, or like a motor that transfers energy into the companion's orbit. On Earth today, the moon's tidal drag is slowly lengthening our day and pushing the moon farther away. In a no-moon Earth, the sun's tides still exist, but they are weaker, so the energy exchange changes. Day length, spin rate, and even how much internal heat is dissipated would follow a different timeline. It should be noted that this is not just bookkeeping, it affects how the deep interior moves. Inside, rotation is tied to another crucial system, our magnetic field. Earth's field is generated by a dynamo effect in the liquid outer core, where conducting metal moves in complex patterns and, combined with planetary rotation, builds a global magnetic bubble. That bubble deflects much of the solar wind and some high-energy particles from the wider universe, helping our atmosphere and oceans survive over geological time. The giant impact that formed the moon probably reshaped Earth's core and set its early spin. Change that event, and you change how vigorously the core stirred when the dynamo switched on, and how strong the magnetic field was at different epochs. In the hunt for alien life, we often ask whether a planet is in the Goldilocks zone of its star, but a long-lived magnetic shield may be just as important for keeping a world truly habitable. So it's time to find out the truth. If we delete the moon from Earth's history, do these subtle shifts in tides, spin, and shielding still add up to a planet that protects and nurtures life, or one that slowly lets its atmosphere, its oceans, and its chances slip away? A quieter night sky, light, impacts, and early life's odds. If we erase the moon from Earth's story, what does the very first night look like? Not the poetic version, but the physical reality of a sky with no bright disk at all. Without the moon, night on this planet is truly dark. Starlight, the faint glow of the Milky Way, and a thin green ribbon of atmospheric airglow become the main sources of light. Coastal shallows, where early life may have crept toward the surface, would swing from harsh daylight to almost complete blackness. This means any organism that used light to navigate or feed would be living in a far sharper, on-off world than ours. On our real Earth, many creatures time their behavior to the lunar cycle. Plankton rise toward the surface under dim light, coral spawn on particular full moon nights, and even birds migrate using the changing brightness of the sky. Take the moon away, and those cues vanish. Biological clocks would still lock onto the day-night cycle, but the finer lunar calendar disappears. In the hunt for alien life, that is a reminder, when we imagine ecosystems on distant worlds, we should not always assume a handy natural nightlight in the sky. There is another, more violent difference. The moon did not just light our nights, it also helped clean up the early solar system. Its bulk almost certainly swept up some of the debris left over from planet formation, and the very impact that created it may have rearranged the orbits of incoming projectiles. Remove the moon, and Earth faces a subtly different impact history. Not necessarily safer, not necessarily deadlier, just different. It should be noted that even with a moon, the young Earth was hammered by asteroids and comets. Without that companion, some simulations suggest a few more objects might strike us, instead of being deflected or absorbed. Each extra basin-carving impact could sterilize large surface areas, boil oceans locally, and reset fragile shallow water ecosystems. Optimistically speaking, that might push the cradle of life deeper underground, or into the high-pressure safety of deep-sea hydrothermal vents. And that darker night helps that scenario. With no moon, the deep ocean becomes an even more isolated environment, shielded from surface radiation bursts and impact firestorms. Microbes around vents would barely notice whether a moon existed or not, yet their surface cousins might be wiped out again and again before they gain a foothold. So, let's begin to see the long-term stakes. A moonless Earth could grow life that knows only a sky ruled by the Milky Way, where time is counted in seasons and stars, not in phases. But does that planet ever stay stable, gentle, and predictable long enough for an intelligent species to look up at that breathtaking darkness and start asking why? Would complex life still emerge, or get stuck at the microbe stage? So if our imaginary observers are standing on this moonless Earth, what kind of world are they actually living on? Because before we can talk about minds and civilizations, we have to talk about the stage they evolve on. Without the moon, our planet spins faster, days are shorter, winds are stronger, and the Coriolis forces that shape storms are more intense. Tides are weaker, and mostly driven by the sun, so instead of dramatic rising and falling coasts, many shorelines barely pulse. Above all, Earth's axis is less anchored. Over millions of years, the tilt can wander, swinging climates from gentle to brutal as ice caps grow, melt, and reappear where tropical forests once stood. It should be noted that this chaos does not mean a dead world. Microbial life is astonishingly resilient. In the hunt for alien life, we constantly remind ourselves that single-celled organisms thrive in boiling vents, deep crustal rocks, and Antarctic ice. On a moonless Earth, oceans and subsurface habitats would still buffer temperature swings. Hydrothermal systems at mid-ocean ridges would keep chemistry running, even during global freezes or supergreenhouse phases. Basic life almost certainly appears, adapts, and spreads. But what about complex life? That is a very different question. Large plants and animals depend on long-term patterns. Forests need stable rainfall over centuries. Coral-like ecosystems need sea levels that do not lurch up and down every few 100,000 years. If Earth's tilt drifts from say 10 degrees to 60 degrees and back again, continents can cycle between deep freeze and scorching desert. Each big swing can act like an evolutionary reset button, pruning complex ecosystems back to simpler, hardier forms. This means that on a moonless Earth, big land animals might repeatedly emerge and then vanish, their habitats erased by shifting ice sheets and migrating climate belts. Coastlines would redraw themselves as ice locks and release as oceans. The long, quiet stretches that on our Earth allowed forests, dinosaurs, and eventually mammals to diversify might be shorter, rarer, or more fragmented. Yet there is another side to this. Evolution feeds on change. Fluctuating environments open new niches, isolate populations, and create powerful selection pressures. During relatively stable intervals between tilt-driven extremes, surviving lineages could explode in complexity, experimenting with new body plans, new metabolisms, and perhaps even new ways of sensing their unpredictable planet. Optimistically speaking, the very chaos that delays complexity could also sharpen it when conditions briefly calm. So, let's begin to see the real dilemma. A moonless Earth could still have forests, reefs, and oceans full of complex life under dark skies blazing with the Milky Way. intelligent species might rise more than once, only to be challenged again by slow, relentless swings of climate and sea. So it's time to find out the truth. Does such a world ever enjoy a long enough, stable enough window for a technological civilization to take root, build a global society, and start asking questions about its missing moon? Civilizations on the edge? Could intelligence thrive here? If the climate keeps lurching between ice and furnace, can anything as delicate as a technological civilization really survive? We know that agriculture, cities, and science all depend on one thing first: stability. Fields need predictable seasons, rivers that do not vanish, coastlines that do not migrate hundreds of kilometers within a few lifetimes. On a moonless Earth, the axial tilt would not be gently pinned like ours. It could wander, slowly but chaotically, over millions of years. The question is not whether it changes, but how fast. Do we still get multi-thousand-year stretches where the tilt, and therefore climate, sit in a relatively calm configuration? If we do, then in the hunt for alien life, those windows might be long enough for farming to take root, for surplus food to support cities, and for written records and technology to snowball. Civilizations might rise in the quieter intervals, then be tested, or even erased when the axis drifts again. But while the long-term background is chaotic, the night-to-night experience would be stunning. With no moon, the sky would be darker, the Milky Way a blazing river of light. Imagine growing up under that, a bright, structured galaxy overhead instead of a single dominant disk. Myths would probably center on the band of the Milky Way, on star clouds, and dark dust lanes. It should be noted that, even with simple telescopes, people might notice fuzzy patches and realize they are other galaxies far earlier than we did. This means that once intelligence arises, astronomy could advance fast, because the structure of the universe is simply harder to ignore. There is another subtle shift. Without obvious monthly lunar phases, early calendars would not have a built-in 30-day rhythm. Timekeeping might lock directly onto the star and the fixed constellations, solstices, equinoxes, heliacal risings of bright stars. Festivals might be annual rather than monthly, trade might organize around longer solar cycles, and the social heartbeat of early cultures could feel slower and more seasonal, even if daily life is just as intense. What about planetary defense? The moon does perturb some impactors, and it certainly bears the scars, but most large bodies in the system are steered by the sun and the giant planets, so the impact risk might change only modestly. The real existential threat is still the wandering tilt, coastlines redrawn, climate belts sliding, ecosystems stressed. So here's the pattern interrupt. Maybe we are asking the wrong question. Instead of wondering whether a civilization like ours could cope with that chaos, imagine an intelligence that evolved inside it. For them, drifting climates, migrating ice caps, and shifting deserts would be normal. Optimistically speaking, their science, their engineering, even their philosophy would be tuned to variability. From their perspective, our moon-stabilized, gently rocking Earth might look like the strange one, a rare, overprotected world in a universe where most habitable planets must dance without such a guardian. And if that is true, what does it mean for how we search the skies for other minds? Exoplanets without moons. Are we overrating our luck? If most habitable planets have to dance without a guardian moon, we have to ask a bigger question. Are we overrating just how lucky we are, or underrating how adaptable planets can be in the first place? In the hunt for alien life, we have now cataloged thousands of exoplanets. But there is something striking about that catalog. Almost none of those worlds comes with a confirmed large moon. This is not because moons are rare by definition. It should be noted that our detection methods are simply stacked against them. We usually discover planets when they pass in front of their star, or from the tiny wobble they induce in that star's motion. A moon signal is smaller, messier, and easy to bury in the noise. There are a few promising exomoon candidates, but they are controversial, right at the edge of what our instruments can pull from the data. This means that when we picture an Earth-like planet in another system, we quietly copy our own Earth-moon setup onto it, even though the odds are that many of those planets actually look more like our alternate, moonless Earth. Same broad size, similar orbit in a Goldilocks zone, but no big companion to hold the axis steady. So, let's begin to connect the dots. A world without a large moon may have a more chaotic axial tilt, seasons that drift over millions of years, and perhaps different patterns of tides driven mainly by its star. That description does not sound exotic. It may describe the majority of potentially habitable planets we have already flagged. Optimistically speaking, complex life could emerge on such worlds by adapting to slow, deep climate swings, just as our hypothetical moonless Earth civilization would. But while some scientists argue that a big moon is a powerful stabilizer, boosting the odds that climate stays in the narrow band where complex ecosystems thrive, others see it as only one ingredient among many: rotation rate. the presence of neighboring giant planets that can also tug on the axis, the internal structure and oceans that can redistribute heat, even the composition of the atmosphere. All of these can keep a planet habitable without a lunar crutch. So it's time to find out the truth. Is a large moon a bonus or a near requirement for long-term stability? Here's the practical problem. When we rank exoplanets as most Earth-like, we almost never factor in moons, because we almost never see them. Yet, our thought experiment suggests that we may be missing a whole dimension of habitability. Future observatories, building on GWS, might not just glimpse exomoons directly, they could infer their presence from subtle timing shifts in a planet's orbit or unexpected patterns in starlight. If one day we confirm a truly Earth-sized moon around a truly Earth-sized planet, how should we treat that world? As just another target, or as a top-tier candidate for oceans, continents, and perhaps mines? And if such systems turn out to be common, does that make our own Earth-moon pair less of a cosmic fluke, or does it raise an even stranger possibility about why we are here at this particular time in the universe's story? So, no moon, no life. Weighing the evidence, so if Earth without a moon is not a simple on-off switch for life, what does that actually look like? If we hit delete on the moon at the very start, what kind of planet are we really left with over billions of years? Let's pull everything together into one picture. No giant impact means a different early Earth, probably spinning faster, with a shorter day and a slightly different interior. With no big companion in orbit to tug on it, Earth's axial tilt would be much less stable. Instead of hovering near 23.5 degrees, the tilt could wander over tens of degrees on long timescales, making ice ages deeper, summers harsher, and climate zones migrate far more dramatically. Tides would still exist, driven by the sun, but they would be weaker, with smaller intertidal zones and less energetic coastal mixing. Nights would be truly dark, with the sky ruled by the Milky Way instead of a brilliant lunar disk. And in the deep past, the impact history, and maybe even the magnetic field, could have unfolded differently, changing how often the surface was reset. So, is that world dead? Probably not. Liquid water, volcanic recycling of carbon, and starlight are the core ingredients for a habitable planet. This means that as long as our moonless Earth still orbits in the Goldilocks zone with a decent atmosphere, basic microbial life is very likely. In the hunt for alien life, we already treat many exoplanets with no obvious moons as serious candidates, because chemistry does not care whether there is a big companion in the sky. But while simple cells are adaptable, complex multicellular ecosystems are more fragile. On a moonless Earth, chaotic swings in tilt and climate could trigger more frequent mass extinctions, more habitat loss, and more evolutionary resets. Optimistically speaking, complex life could still arise during long, relatively stable intervals, just as it eventually did here. It should be noted that even on real Earth, complexity took billions of years to appear and survive. Add extra chaos, and the odds of uninterrupted progress shrink. Where the moon may really matter is for technological civilizations. Civilizations need long, stable windows to develop agriculture, cities, and global infrastructure before the next catastrophe. A moonless Earth might still produce intelligent species, but their history could be more stop and start with flourishing coastal societies wiped out by climate whiplash or impact events that our real moon partly deflects. So it's time to find out the truth about our cosmic luck. The moon looks less like a strict requirement and more like a probability booster, a stabilizer that quietly raises the chances that complexity can accumulate and persist without being erased. Yet our models of obliquity chaos, tides, and early impacts still have large uncertainties, so we cannot yet put a precise number on how much the moon changed our odds. Which leaves us with a deeper question. If the moon is helpful, but not absolutely essential, how should that reshape the way we search for life on distant worlds, and the way we think about our own place in the universe? In the next section, we will have to confront an even stranger possibility about what our moon might really be telling us. Your verdict on the moon, redefining Earth-like together, so it's time to find out the truth. If we strip everything else away, what did we really do in this episode? We deleted the moon. We rewound Earth's history to that ancient giant impact and asked, what if the debris never gathered? What if our sky stayed empty? We watched the planet spin faster, its day compressed. We let its axis wobble more, seasons lurching over millions of years. We quieted its tides, slowed the mixing of the oceans, and then followed the consequences for climate, for ecosystems, for the long, fragile climb from chemistry to life, and from life to minds. And after all of that, one question still stands. Could a world like that still give rise to a civilization asking these questions about the universe? Or did our moon quietly push us over a threshold that a billion other planets might miss? This means the verdict is no longer just ours. In the hunt for alien life, should a large moon be part of what we really mean when we say Earth-like and habitable? Is a stabilizing companion, raising strong tides and slowing a planet's spin, a near requirement for complex life, or simply one of many possible paths, no more special than any other cosmic accident? It should be noted that the data we have, even for our own system, are incomplete. We have one Earth, one moon, one history. So, let's begin something different. Let us turn the question over to you. If you were drawing up an official habitability checklist for distant worlds, would a large moon make the cut, alongside a stable star and a comfortable Goldilocks zone? Or would you leave it off and trust that complexity can emerge even on a wildly wobbling, moonless Earth-like planet? Here is a more personal angle. Imagine a civilization that grew up under a truly dark night. No phases, no eclipses, no obvious clock in the sky. Would their myths be different? Their calendars? Would they notice exoplanets and other stars sooner or later than we did? Tell us in the comments whether you think a moonless Earth civilization would see the universe in a fundamentally different way from us, and why. Optimistically speaking, our journey does not end with the moon. Next, we will explore other near-miss Earths, a world like ours orbiting a restless red dwarf, a planet spinning twice as fast, a lonely rogue world adrift between stars. Each scenario will force us to redraw, once again, what we think a truly habitable planet can look like. So the next time you see the moon hanging in the sky, pause for a moment. You are not just looking at a pretty disk, you are looking at a quiet architect of our history, a companion that may have nudged Earth toward minds able to ask these questions. And somewhere out there, a billion moonless Earths may be waiting for their own chance at a night sky full of questions. If you want to keep redefining Earth like with us, make sure you are subscribed, share your verdict on the moon below, and stay with this channel as we follow the data to the next strange version of our world.